Okay, so I think we should start, or rather continue with Salim, who will tell us about modularities and special cycles, part 2.
Great. Well, thanks, Jonathan, for the introduction. Thanks everyone for coming back. So this is the second part of lectures that I started last week, and let me just recall where we stopped last week. So the best joined us have all context. So the situation is the following. Let's take L comma Q via quadratic lattice. So I mean a lattice endowed with a quadratic form. Z is isomorphic. L is isomorphic to Z to some power. In my case, it's going to be n plus 2. Q is a quadratic form, which will have a signature n comma 2. And I introduced the following period domain, which are the set of lines in complex lines in the compactification of L, which are isotropic under this pairing, and which satisfy this negativity condition, which omega paired with omega bar is negative. So this was the period domain, and it parameterizes Hodge structures of weight 2 on this L that are polarized by Q. Okay, now the choice of a subgroup of orthogonal group of this quadratic form, so some subgroup that preserves L, will act on this space D, and the quotient is in fact, it's an algebraic variety. It's an orthogonal Shimura variety. So the spaces appeared as like the examples we saw last week is that whenever you have, let's say, for example, a family of K3 surfaces, then you have a period map from S to D mod gamma. And so this is the map that's associated to any fiber here, the Hodge structure, which are parameterized by this D mod gamma. So these are the setup where this spaces appeared. And I introduced a generating series on the spaces. So for every m at least 1, Z of m was a codimension 1 divisor in D mod gamma, and then for M0, Z0 will take it just the dual of the Hodge bundle. And so the upshot here is that we can do the following generating series, which takes into account all the ZMs together, due to the power term, sum over all m at least 0. And let's call this the theta series of L. And so this is now valued in the Picard group. So like, say we're taking the classes of these divisors in the Picard group, D mod gamma, when I join this formal variable Q. Okay, so this is like the generating series that I introduced. And the theorem of Kudla and Milson is that this generating series is in fact is a holomorphic modular form of weight 1 plus n over 2, and the level, some level gamma, some congruent subgroup of FL to Z. Okay. And in fact, the ZMs are the noted left-shift cycles. So when you pull them back to any, like say you have a family of K3s, you pull back the ZM to S. This gives you exactly the noted left-shift locus in this family. All right. Now we saw one example last week where somehow this theorem does not have any content. So we're going to see another example today. So two examples. So example one, and this is from last week, where if we take the lattice L cubed to be just the direct sum of two hyperbolic planes, so where the intersection matrix here is just 0, 1, 1, 0. So this is of signature 2, 2, 2, 2, and it's unimodular. And in this situation like this, Shimura varieties are just identified some appropriate choice of gamma to the product of two modular curves that you can embed now in the compactification. And this generating series, theta L, in fact, if you just look at it in y1 cross y1, it's just going to be 0 because there's no, the pk here is going to be trivial. But if you look at it in the compactification, this is where interesting things happen. It is going to be equal to -1/12, the Eisenstein series E2 times the line bundle O11. So it is not a modular form, but it's what we call a quasi-modular form. Another way of writing this is the following. If you take ZMs in this compactification and then you subtract, well, in this case, you add 1/12, the n Eisenstein series coefficients of E to n times the cycle. So O11, you can choose a cycle that represents O11, and it's going to be just infinity cross x1 plus x1 cross infinity. And so these are the boundary cycles in this compactification. And so by doing this correction, by correcting this CM by boundary cycles into, if you call this new cycle Z hat M, the generating series of the Z hat M becomes, you restore the modularity property, is a holomorphic modular form. In fact, this is a little bit trivial because it is just 0. It's trivially a holomorphic modular form, but I chose to write it this way just to give a motivation for the conjecture of Kudla. And the second example.
I'm asking you to explain this. You have to be careful about stacky issues here with the y1 and x1.
So, yeah, I'm talking the quartz spaces, and that's why. So they're taken into account when I identified the Z of M's to
So you're adjusting for it.
Yeah, I'm adjusting for it. Yes, exactly.
Is that where the 1/12 comes from?
What?
Is that where the 1/12 comes from?
Yeah, exactly. I also like why you have this 1/12. So there's some things you need to check, but yes, there's.
So if you did it with Y2 from the start, you just end up with.
So okay, if you did it with Y2, if you introduce some level structures, yeah, it's not. You're saying you will not have.
Or will it just all go away, or will it become all? I mean, what?
Oh, you mean the modularity property? If you introduce.
Well, if still be.
Yeah, you could obtain like some, for example, I mean, the lattice also that I chose is very special. Like it's a unimodular lattice, meaning that all the modular forms that you're going to obtain will be for SL2Z. And so, but then SL2Z weight 2, there's going to be none. Okay. Now, if you choose a lattice which is not unimodular, then this group gamma automatically going to be smaller, and so you're introducing some level structures, and there is going to be some interesting cohomology.
And you'll probably get them.
You'll probably get something. Yes, exactly. Yeah. But in this case, it's like not. And the second example is when the lattice now is of signature 1, 2. And again, let's say assume it's isotropic. Then you get in this example just the modular curve is the Shimura variety, and the cycle Z of M's will be just some cycles of CM elliptic curves. With like a special endomorphism, trace 0 endomorphism of square F. So if you do this generating series, you recover like a generating series that's been considered by Xavier, the sum over all M at least 0 of H of N Q to the N. At least if you compute like the degrees of this 0 cycle, where this H of M is just the number of binary equivalence classes of binary forms, so positive definite binary forms of discriminant minus n. So yeah, again, this series here is not, I mean, if you consider again the generating series of this cycle just in Yn, you just get 0. But when you're taking degrees, like implicitly, like you're considering in the compactification, if you look at them in the compactification into x1, and then the generating series in cohomology is just going to be the generating series of their degrees. And this is not, so F plus is not a holomorphic, it's holomorphic, but it's not a modular form. But what Zaghi proved is that it has a particularly nice expression by like completion by a non-holomorphic part. Let me just write the expression of the non-holomorphic part. It's the 1 over square root of y times the sum over all the integers mz beta or pi m squared y exponential 2 pi m squared tau. Okay, so y here, so I'm writing just tau as x plus iy in the Poincare half space, so y is just the imaginary part, and beta is just this integral, this function beta of t is 1 over 16 pi integral from 1 to infinity of u to the power minus 3 halves exponential minus ut u. Okay, so once what Zaghi proved is once you do this completion, now this new function here of tau transforms like a modular forms of weight 3 halves. And level gamma 0 form. Okay, so the original generating series is not a modular form, but it admits some non-holomorphic completion that makes it transform like a modular form of weight 3 halves.
Is it always the case that these non-holomorphic guys, if you look at them along like a unipotent, like a fixed y coordinate, just the x-axis, you get negative Fourier coefficients, so you keep the positive ones the same?
In this case, yes. In this case, it's going to be true. You're getting negative Fourier coefficient. You mean like in here?
Yeah, like instead of E of nx, anything positive or negative, it's just like you're only adding negatives. Listen.
So I think I should write here not tau, but y. I mean, there's not.
X maybe, or you would mean y? It's a function only of y?
Well, it's it has to converge. I think 1 second. Okay, no, I think I wrote in my document tau, so let me just keep it tau. But okay, there's there's some estimate here on beta of t, like the way it decreases to make it converge. Yeah. Okay. Sorry. So what's your question, Jacob?
Yeah, I wasn't more about convergence, but saying I'm trying to understand the holomorphic part. If you have the holomorphic part, right? You have q to the m for m positive.
Yeah. Yeah.
Yeah. So that's on horizontal like lines. If you get a periodic function, right? Because it's varied by adding 1, so you can have a Fourier expansion.
Yeah.
And it seems like you only get positive Fourier coefficients. And I'm wondering if the non-holomorphic part is only ever adding negative Fourier coefficients.
Adding negative Fourier. So
well, it seems like it's negative, right? It's e to the minus m squared.
Right. So yeah. So I think there's only going to be negative Fourier coefficient because there's an operation that you can do, like which you can take the derivative with respect to tau bar, and then you just get an honest theta series with positive coefficients. So I think that seems true that you only. I don't want to like commit too much to this response. All right. Okay. So these are the two examples where this Kudla modularity theorem does not tell you anything on the nose. Like you have to do when you do a compactification, you get something completely different from what the theorem says. So this motivate this following conjecture by Kudla. Is that there exists some compactification of D mod gamma which is smooth and projective. So it's going to have some boundary component, like I'd say some SMC compactification on the boundary component, like some union of divisors, finite union of divisors, such that well, there's some recipe for like correcting the cycles uniquely using like this boundary divisors. So for each I, there's some coefficient A of n times bi, and the sum over like this finite sum over this boundary divisors, such that this new cycle here, z hat of m, the generating series of this z hat of m, q to the m, is again a modular form of with 1 plus n 2 and some level gamma inside S2C. All right, so in these two examples, this correction you can just take, like in the first example we saw, you can just take this correction here, and then the resulting modular form is just going to be 0. So this theorem there is obviously true. And then in the second example, you can do the same thing. You can just correct the cycle Zm by Hm times the point at infinity. That you can declare it as your correction. And then you get again, this generator just becomes 0. Okay. So in these two examples, like the corrections are almost trivial. I guess what's an interesting part is what these corrections look like So, or the coefficients of this correction themselves are part of either quasi-modular forms or these are in fact this is what's called a mock modular form, this holomorphic part. So it's at definition of a mock modular form, it's a holomorphic function that appears as the holomorphic part of a function that transforms like this. So a non-holomorphic function that transforms like this. Okay, so the general answer I will give today shows that the behavior is going to be a mixed, or a mixture of these two examples. So the theorem, and this was with Angle and François Greer itself, 123, is that, I mean, this conjecture is true. And I will give an explicit compactification and explicit correction. Okay, so that's the goal of the course. Stop today. Any questions? All right, so the first step is to compactify this D-mod gamma. Okay, so this is classical theory of compactifications of Shimoda variety. I mean, the first interesting compactification is the Bailey-Borell compactification. And so how does that work? Well, we can look at D inside D bar, which are now just a set of lines that are still isotropic with respect to the quadratic form, but I will relax the negativity condition, this large inequality, omega large at most 0. And the story is very similar to how, maybe if you've seen before, how you compactify the modular curve, like you look at the upper half space, you take its closure inside P1. So this is add in this line here, like the real line, and then add in the point at infinity. And then you're just taking like the rational points of this in this closure and this boundary. So you're taking like all the rational numbers here, and then you're doing some equivalence relations. So it's the same thing here. We're not going to take this whole closure, but rather just the rational, some rational boundary components, which are determined in the following way. So there is what I would call type 2 components, which are obtained by the data of a totally isotropic rank 2 submodule L. So this is a rank 2 totally isotropic. So it may or may not exist, but quadratic form having signature n comma 2. 2 is the maximal dimension of a possible, like a totally isotropic subspace. Okay, now for each j like this, I will have a boundary component dj, and dj is just the lines that are contained in this like totally isotropic lattice. Okay. And the second, I should add a condition, which is that yeah, I'm sorry. So if I choose a basis of Tj as Z alpha plus Z beta, then more specifically, I'm looking at all alpha plus tau beta for imaginary part of tau, not but you can even take it positive. And so in this description, it will just identify it to a copy of the upper Hall space. So that's like the point I would like to make is that all these DJs will be isomorphic to a copy of the Poincare upper Hall space. So they're like one-dimensional. And then the type 3 component will be just parameterized by rank 1 isotropic lattice or isotropic lines. And for this type of every time you have a rank 1 isotropic line, you can just take di to be just the line that corresponds to, this isotropic space. It's obviously satisfies these two conditions. Okay. So the group gamma will act. I guess I could take the union over all such j's or the union over all such i's. So d gamma baby Borell is just d then union over all the rank 2 isotropic sublattices and then the rank 1 isotropic sublattices quotient by gamma. And this is the Bailey Borell compactification, and it's a projective algebraic variety. All right, so from the point of view of Hodge theory, like maybe that's the interesting thing to one interesting aspect of this compactification is that this type 2 and type 3 parameterizes the way the way 2 Hodge structure degenerates. Okay, and that's where the name comes from. That's why we call them type 2 and type 3. So
Is there no type 1, by the way?
this is just D.
Okay.
Okay, and here's why. Like, you can also call it type 1. So imagine you have like a family of K3s over a punctured disk. And then the lattice L is just the primitive cohomology of a nearby fiber along with its parent, so primitive homology nearby fiber. Then the pi1 of the base acts on this lattice. This is just the monogamy action. And it is a theorem that this, like the pi1 of delta stable is generated by a single element, like a clockwise, anti-clockwise loop. And so it maps it to some element T in the orthogonal group of this lattice. And in fact, this element is always quasi-unipotent. That's a theorem of Borell. Now, if you consider n, let's assume it up to some finite base change that this element T is unipotent. Okay, assume it's unipotent. Then n being defined as the logarithm of T. Because T is unipotent, this logarithm will be just like a polynomial in T minus identity. This will be nilpotent And it will be an equivalent either of order 1, order 2, or order 3. These are all the 3 possibilities. So the order 1 case, in fact, it just means that n is equal to 0. And what that means is that this Hodge structure extends across the puncture as a pure Hodge structure. The family of K3s might not. There's some jokes about that. I guess you have to base change or something. But it means there's a pure Hodge structure on the H2. The order 2 and order 3 are what corresponds to what I call the type 2 and type 3. And here, when you have a monodromy operator, you have a filtration associated to this monodromy operator, like the monodromy weight filtration or the monodromy filtration. And the piece of this filtration, in fact, will just be the steps of this filtration will be given by J per bar L, where J is an isotropic rank 2 lattice. And so this is like why they call type 2. And then type 3, the weight filtration that you obtain is given by this I, and this I perp, and L, and I is an isotropic rank 1 lattice.
Isn't n still order 2 in the third example?
Order 3. Because it's not 0 restricted to I perp. It's a whole.
But it takes L to I, doesn't
it? It takes I perp to I, but not. I don't think it thinks L to I. It has.
But it lowers weights by 2, right? You're saying the weights are 0 through 4.
The weights are 0 through 4, yes. And okay, I did not tell you which pieces lie in which. So you have W0, W1, W2, W3, and W4. And okay, the W4 is going to be L. There's not going to be the graded pieces at 1 and then 3 are going to be trivial. You're going to have a graded piece at W2, and it's not going to. Yeah, sure. In fact, the fact when you restrict it to I perp is going to appear a little bit later. The fact that it's non-zero determines like the Borell compactifications. Yeah. But yeah, question. So here the point is that this Bailey-Borell compactification parameterizes like this the appearance of this copy of the upper half space should be thought of as the fact that this or at least this J inherits a weight 1 Hodge structure that makes it the Hodge structure of an elliptic curve. And then that copy of the upper half space remembers this weight 1 Hodge structure here. Here, like all the graded pieces will have trivial Hodge structures, so there's nothing to remember. That's why there's only a point. And that's a general philosophy is that the Bailey-Borell only remembers the Hodge structure and the graded pieces, which in this case, the only graded piece is J, which have weight 1 Hodge structure, and here all the graded pieces are Hodge state, so they don't have any interest in Hodge structure. Okay, so I just wanted to give like a brief, maybe dictionary between this compactification defined that way and the point of view of degenerations of Hodge structures. Any questions? Now the defects of the Bailey-Borell compactification, it's not compact. It's not compact, it's not smooth. And to get a smooth compactification, we will consider the Borell compactifications. So these were considered by Ash, Mumford, Rappaport, and Hai. And the way they're constructed is, so there is a, so it's a smooth compactification. So like it's a, I would call it d mod gamma sigma. It maps to baby Borell. And the boundary of this compactifications will depend on the equivalence classes of rank 2 isotropic lattices, and so Bj, and rank 1 isotropic lines with an extra data that I will now describe. So there's still something here. So let me just describe what do you get? Like what's the structure of the boundary? Like what boundary divisors are in the first case, like when you have a rank 2 lattice, sublattice, which is isotropic. So you fix J inside L, totally isotropic of rank 2. So one way to think about this smooth toroidal compactifications is that not only they remember the graded pieces, but they also remember the Hodge structures, or like the Hodge filtration, the whole mixed Hodge structure. And of course, the graded pieces is just some information of that. And so this Bj will be just, so we said that this J will inherit like a weight 1 Hodge structure, and those are parameterized by the modular curve of some level. And then there's still this extension. Let me just write it here. So there's J, J perp, and J perp mod J. There's still an extension. This is like, will be completely Hodge state, weight 2, like there's no, like it's Hodge state. And this is like weight 1. And so there's an extension of a Hodge state structure by a weight 1 Hodge structure. And these are parameterized by this tensor product, or like this tensor product of the universal elliptic curve with this lattice here, J perp mod J. So this is a rank 2, or like n-2 lattice with a positive definite quadratic form. And this is just a Kuga-Sato variety over the universal modular curve. So it's e to the power n-2 non-canonically. And so this universal family is the boundary divisor that corresponds to this rank 2. Okay? That's all that's important. This point is just to make the connection to mixed Hodge structure on the degeneration. Now, the type 3 boundary divisors will depend on the so-called like cone decomposition. So for the type 3, so you have now I inside L are rank 1 isotropic. And I perf mod I, I call this lattice A, will have a signature n-1, 1. Okay, so it's a Lorentzian lattice. So inside this lattice, there is a cone of vectors that have a negative norm. And the Borell compactification depends on a choice of what we call a cone decomposition, like a rational cone decomposition of the C, which is just polyhedral. So this cone looks like this. And then we have like some polyhedral cone composition, which is gamma, like invariant under the orthogonal group of K. So the point here is that, let me just recall this picture here for the modular curve. When you want to compactify the modular curve, if you choose an imaginary part of y big enough, then like bigger than a certain range A, this piece here, you can embed it up to the quotient, like when you quotient by z, you embed it into like a punctured disk, which itself can be embedded into a C star. You can see it inside a C star. And so there's a similar picture here where like this D, you can quotient like take the quotient by an intermediate, an intermediate group gamma tilde, where you embed it in a certain C star to the n, like near this like this type 3, when you're approaching like this type 3 cusp. And now this cone, in fact, tells you in which direction this d mod gamma points inside the C star to the n. It's like some indication or where this like lands here. It's the same way like you're able to say this delta star inside C star. Okay, and now this choice of the sigma determines a partial compactification of this toric variety. So that's roughly the idea of the construction. So, okay, if this is like, never seen this thing before, the point to take home is that for toric varieties, like the boundary divisors are determined just by the rays of this cone decomposition. And so, for each gamma, or like little gamma here, in this cone decomposition, so for each gamma, which is a ray in the cone decomposition of C, we get a divisor I gamma, which is a boundary divisor of d mod gamma in d mod gamma Z. So these are well, now the picture is complete. This is how all the boundary divisors are constructed. So this boundary divisors here admits like they come from toric geometry. That's the important point here. Okay, now we have the boundary divisors. Now we have to understand how to correct the special cycle ZMs. So for this, for the type 2, what I'm going to do for each J rank 2 is the topic. I can consider the theta series of the J third mod J, which is the lattice was rank n comma 2. J third mod J will be positive definite of rank n minus 2 comma 0. So this is just the usual data series that I introduced last time for positive definite lattices. It's just the sum over all j per mod j of q to the power q lambda. Now, there's something wrong here, which is that the fact that the weight here is n minus 2 divided by 2, so n over 2 minus 1, and we are aiming for some correction of weight 1 plus n over 2, so there's a discrepancy of 2. You're right. And then the second actor is when I is rank 1 and omega is a ray in the, gamma is a ray in this cone decomposition. Then the orthogonal to gamma inside A is a lattice of signature n minus 1 comma 0. So this is again a positive definite lattice, and I can consider its data series which has signature, which has weight n minus 1 over 2. So it's a modular form of weight n minus 1 over 2, and again it's different from 1 plus n over 2 that I'm looking for. That's okay. That's the restate the theorem. Is that if I take the Zariski closures of the special cycles, and then I add 1 over 12, the sum over all the gamma equivalence classes of the rank 2 isotropic lattices of E2 times the theta series j per mod j. Now this times the boundary divisor bj, and then minus minus 1/2 the sum over all I and gamma up to like equivalence under the arithmetic group of the Zakier series that I introduced earlier, like a slight modification of it, times the theta series of I per mod I times the boundary divisor bi gamma. Then this correction here, now this new corrected theta series, is the object I'm looking for, is a holomorphic modular form of weight 1 plus n over 2. Okay, and let's make sure that the weights match up. I said that this has weight n over 2 minus 1. E2 has weight 2. So when you multiply two things, you add their weights and you get weight 1 plus n per 2. So this matches up. And then the Zaki series has weight 3/2. This has weight n minus 1 divided by 2. So when you sum them, you get indeed something with weight 1 plus n per 2. So all the weights match up. Okay, so how does that answer Kudla's question? Well, I mean, if you take the Fourier coefficients of this expression, then you're taking a correction of Zm by the boundary cycle Bj and the boundary cycle Bi gamma using coefficients of this two Q series. In fact, the proof we really see appearing the coefficients in this Fourier series as counting Hodge classes at infinity. This is really another interpretation of this correction. Like the ZMs are counting how many Hodge classes we have on the fibers in the interior, and this corrections are counting how many Hodge classes there are.
So you mentioned there's a risky closure.
Of ZMs, yes.
Are they not closed to begin with? Or you're closing them to the boundary?
Yes, to D mod gamma sigma. Yes. Yeah. Yeah.
And so here it's sort of neither quasi nor mock. I mean, you need to do both.
Yes. Yes.
Because I thought that they were sort of equivalent somehow.
So yes, I mean yes and no, depending like how I think that the convention is that E2 is not considered a mock modular form
Uh-huh.
and Zagi is considered a mock modular form. So this is like what referred to as a quasi-modular form and this
Right,
is a mock
because
modular
it's-
form. Like the correction, so to make
The mock
E2
modular form is holomorphic but not modular.
yes.
And the quasi thing is modular but not holomorphic.
No, it's both are holomorphic and not modular form.
Ah,
But E2, I mean, this is E2, you just correct it somehow by 3 over pi y or something. So like the correction is just concentrated in a single term.
I see.
And then the bigger one, you correct it by this big series. And in fact, here we see appear in the two behaviors. So like in the case where we were in 2, 2, this term, we did not see this term, we only saw this one. And then in the modular curve case, we did not see this term, we only saw this term. So the general case is a combination of both behaviors. Okay.
But your theorem is just like, here is what it is, yes? It's not surprise something is modular, it's like we've computed it.
Well, I'm saying that this is a holomorphic modular form. I'm not saying it's zero or anything.
Okay.
Yeah. Like, of course, if you, let's say, okay, if you, let's say, take an example where.
And this is in Chow, right? Or you're working in cohomology?
So, actually, the theorem is in Chow.
Chow.
Yeah. So let me say in Chow, if n is at least 3, or if n is at least 2 and the lattice gamma is irreducible. Avoid situation for products. Basically, the case where super rigidity holds in this case. Okay, so let me just do an example to see how one can use such statement. Suppose you're given a family of elliptic K3s with a section. So the fact in this situation, we know exactly what's the transcendental lattice will be in this family is just 2 copies of the E8 lattice. So the unique E8 is the unique even unimodular lattice rank 8, and 2 copies of the hyperbolic plane, so the plane with intersection matrix 0, 1, 1, 0. So this has a signature 18, 2. And it turns out that the type of isotropic planes that could appear are like the J-curve mod J that could appear would be isomorphic to E8, E8-2. And so this theta series, J-curve mod J, will simply be the unique modular form of weight 8. And so it has to be E4 squared. And so this term here is completely explicit in that situation. And okay, this term here will depend on the degeneration and like the configuration of the singular fibers. But let's say if you had only like type 2 degenerations, that second term will not appear. And the result, this theta L hat, will be a modular form of weight 10. So it's necessarily equal to a multiple of E4 times E6. And of course, the way you find this multiple, you just look at the constant coefficient, and it pins down completely like all the intersection numbers of this S with the Noether-Lefschetz cycles. And so that's a way of computing all like the Noether-Lefschetz number of this family. Okay, so that's one way this theorem could be used. Okay, so in the remaining time, let me just give maybe an ideas of the proofs of this specific theorem. The second theorem that I will not talk about today for unitary Shimura varieties, I will talk about it next week in the number theory section. So today only orthogonal Shimura varieties. Okay, so how would we prove such theorem? Well, in fact, the proof is like basically just intersection theory and Poincare duality. And so the starting point is to notice that if you want to prove that this generating series is a modular form in cohomology, we just have to test it against two cycles and prove that all the test results are modular forms. And so we want to test it against H lower 2, D mod gamma sigma, say with Q coefficients or R coefficients. And now the nice observation that appears in this codimension is that any cycle here, we can write it as a cycle that's supported in the interior and a cycle that's supported at the boundary. So if you start with a cycle C here, it's a sum of a cycle in a non-unique way, probably, but at least it's like the homology is generated by the homology of the interior and the homology of the boundary. So a very nice situation. And then if you intersect this generated series with a cycle that's entirely supported in the interior, then this is no different than just the pairing with the original one, simply because the C1 will pair trivially with all these boundary components. So you reduce to the interior part, and in the interior part, we know this is a modular form by Kudla. So it's enough now to understand what happens when I intersect this cycle with C2. Okay, so this intersection with C2 will have, there's like three components, right? There's the first, the intersection of the Zariski closure of the ZMs with C2, and then the intersections of the BJs with C2, and then the BI gamma with C2. And so we have to understand what are the three intersection numbers. So the first intersection number is in fact the most interesting one. And this for a fact, we use like an explicit C2 among like a generated set of the boundary of like the homology of the boundary. And then in this toric variety picture, we can entirely describe this cycle Z hat n as just some cycles like that are used using character like the toric geometry, like character convergences, using the co-character of the toric variety. And so I guess what I'll not be able to tell you exactly like how this computation is done, but at least the formula is very explicit. Like the sum over all this m's of the z hat m's intersecting with C2 will look like a theta series on this lambdas in this lattice K, where K is I not I. Okay, I should say that the C2 among a generating set of the homology of the boundary, but then we can choose the C2 in one of the boundary components that corresponds to a certain isotropic one lattice, and so they're all parameterized by this i's. And so when I am in this part of the boundary, the sum would look like a theta series over the lattice K of some piecewise linear functions, q to the power of q lambda. And these are like some piecewise linear functions who are not, who changes. So piecewise linear functions, it's sum of absolute values of some linear forms, and like the region where they are not differentiable are exactly the rays of the cone C. And somehow it makes sense because if you think about it, this in terms of Hodge loci, the only Hodge loci that's going to appear near the boundary have to be in this I, like parameterized by lambdas in this hyper model. Okay. And then there's a really beautiful theory of just piecewise linear functions, like that you're summing over a Lorentzian lattice and how they produce modular forms. So the idea is that one can find a smooth approximation of this piecewise linear function, such that the result here is just like a C infinity function. And this P lambda satisfies really a specific set of differential equations that are determined by the Borell representation. The punchline is that the generating series of the P lambda itself will be some non-holomorphic modular form. And so this correction has to be chosen carefully. And so now this holomorphic part, or this generating series, is just the holomorphic part of this non-holomorphic function. And then to finish the arguments, so what we've shown roughly is that this z hat, this intersection number of the z hat z tilde MC2, if you add something non-holomorphic, it transforms like a modular form. Okay. Now, for the other two contributions, we prove similar results. If you intersect this BJs with C2 times like the theta series that I wrote in the theorem, and same with the I gamma, you intersect them with C2. We just use the known completions that makes them a modular form. And now when you sum them, all this non-holomorphic part end up canceling out. So the final sum will be a modular form, and it will be holomorphic. And that's like how the argument goes. All right, let me just start.
Any questions? How do you upgrade this to the chow? Can you say anything a little bit about that?
So chow1, you just use the exact sequence, like from chow1, like which is pick to H2, and the kernel will be trivial for n bigger than tiny
Oh,
by
this is the
super
same.
rigidity.
Yes. I see. Okay.
Yeah.
So can I ask for some intuition about why these are modular forms, or how should I think about the fact that these are modular forms?
So, so for the interior part, it's really like explained by this how duality, like from the Veil, like representations, where I guess like the basic question is why theta series of a lattice is a modular form, right? And that ultimately relies on the Poisson summation formula. And that's like the arithmetic theta lift. And now in this geometric situation, there's this geometric theta lift where the modular form that you construct are no longer theta series sum just over the lattice of numbers, but they are theta series of cycles. And you have a similar phenomenon with Poisson summation. Like the original proof of Kudla-Milstein is to show that the ZNs are represented by some specific type of differential forms, such that the generated series behave well under the Poisson summation, and so you get that is a modular form. That's why you get, at least on the interior part, the generation series are modular forms. You should think about it as like some geometric incarnation of the classical theta series for positive definite lattices.
Other questions? All right, if not, let's think again.